In this video, I introduce a diffusion-based world model. Diamond combines a diffusion model and a world model to train reinforcement learning agents to find the optimal policy on sequence of problems of environment dynamics. The environment is modeled as a partially observable Markov decision process, as shown here, where S is a set of states, A is a set of actions, O is a set of image observations. The transition function T describes the environment dynamics P, and the reward function R maps transitions to rewards, as shown here. Agents cannot directly access states ST and only see the environment through image observations XT, emitted according to observation probabilities P, described by the observation function O. The goal is to obtain a policy pi that maps observations to actions to maximize the expected discounted return E. A diffusion process is discretized as margins P and tau with the boundary conditions P0 and Pt, where P prior is a tractable and structured prior, for example, Gaussian distribution. The forward diffusion process is described as a stochastic differential equation, as shown here, where W is a Wiener process, F is a vector-valued function acting as a shift coefficient, and G is a scalar-valued function known as a diffusion coefficient of the process, as shown here, this forward process. A generative model maps noise to data gradually, and the reverse diffusion process is defined as here and shown here from noise to data, where W bar is a reverse time process and the gradient is a square function. F and G are defined to estimate the unknown square functions associated with the margins P tau along the process. A square model S theta is defined to estimate the unknown square function. The diffusion model estimates the square function from data samples without the knowledge of the underlying square function. To access samples from the marginal P tau, the diffusion model needs to simulate the forward process from time 0 to tau. If F is fine, the diffusion model can analytically reach any time tau in the forward process in single step by applying a Gaussian perturbation kernel P0 tau to clean data samples. The denoising square matching function is defined as here and explained in this figure, whereas the expectation is over diffusion time tau. Noise the sample X tau sampled from P0 tau obtained by applying the tau level presentation kernel to a clean sample X0. Since the kernel P0 tau is known in Gaussian distribution, the denoising objective becomes the L2 reconstruction loss as shown here. With the reparameterization, data d theta is calculated from S theta and X tau, where sigma tau is a variance of tau level perturbation kernel. The diffusion world model is a conditional generative model of the environment dynamics, which combines the diffusion models in a world model to train reinforcement learning agents. For PO, Markov decision process, the Markovian state ST is unknown and can be approximated from the past observations and actions. The diffusion world model estimates and generates the next observation directly condition on diffusion model on this history. The modified objective is written as here and explained in this figure. The reinforcement learning agent is used for data collection. And the diffusion model is equal to understand the environment dynamics. And reinforcement learning is used to find the optimal policy. During training, a trajectory segment is sampled from the agent replay dataset under the next observation. X t plus 1 tau is obtained by applying the tau level perturbation kernel. To sample the next observation, the diffusion raw model iteratively solves the denoising diffusion model. Considering the perturbation kernel as a normal distribution as shown here, where sigma tau is noise schedule, the shift and diffusion coefficients F and G are set to be 0 and this formulation. D theta is represented as here, where F theta is a neural network, YT tau includes all conditioning variables, and the preconditioners are computed from these formulations. Where sigma data is the standard deviation of a data distribution. The training objective is written as here. The first term is a network prediction. The second term is a network training target. The vector field F theta is modeled by using a U-net with a buffer of L past observations and actions as shown here. The past observations are concatenated to the next noise observation X t tau as shown here and here. And the actions go through the adaptive group normalization layers in the residual blocks of U-net as shown here. A separate model R psi consists of CNN and LSTM layers to find the policy pi phi using the xt tau as input, as shown here. The agent only interacts with the real environment for data collection. After each collection stage, the current world model is updated by training on data collected so far. The agent is trained with reinforcement learning in the updated world model environment, and these steps are repeated. For more details, please check with these references. Thank you. Bye.